Analytical methods to evaluate the heat transfer coefficient, the convective one, are very limited to a few cases. Therefore, we are using mainly experimental data to evaluate the H or develop correlations to find H of X or the convective heat transfer. And that's what we refer to the empirical method. So analytical solutions find H are limited, and we use experimental data to develop empirical correlations. And we use dimensional analysis and other analytical techniques to find out the relationship between the data that we have collected. Now, let's say in terms of the parameter problems, we can write out, let's say we're going to find the Nusselt number, or the target is Nusselt number, let's say average. It can be written in many forms, but some experimental data are guiding that's going to be some constant. It's going to be a function of Reynolds number to some power of m, Prandtl number to some power of n. Now we can use, I said, dimensional analysis graphical techniques to find out, let's say, the constant of Cmn from the experimental data that we have. So let's say for this specific format, if we plot Nusselt number of L versus Reynolds number of L for a fixed value of Prandtl in a log-log scale, what we are going to get is a straight line. So let's say this is log of Reynolds number, and this is log of Nusselt number. Then what we are going to see here is, for let's say one set of experimental data for specific, these are, let's say, experimental data that we have collected for that, and this is going to give us the fitted line is going to be a straight line, and the slope of that is going to give us m. The intersect of that is going to give us information about C and N here. And let's say if we do another set of experiment with a different Peclet number, then the fitting would be again another straight line. The slope is going to be m. So let's say this is for one Peclet number, this is for another Peclet number, and we can repeat that. Or we can, if we do it for different Peclet number based on the correlations that we have, if we plot, for instance, this is the log of Reynolds number, log of Nusselt number L divided, let's say, by Prandtl number N. So plot of Nusselt number versus divided by Prandtl to the power of F versus the log of Reynolds number, all these curves are going to collapse. So we would see collapse of all data into one single curve. So what we would see are these collected data, the other collected data, and then let's say this is going to be the fitted line here. So these are really like the graphical chart to find out the values of C, N, and M, and based on that we can find out the correlation for Nusselt number in the form of Reynolds number, L, Prandtl number, keep writing Peclet number, Prandtl number to the power of N. For example, let's say through empirical data, the previous formula that we were looking at was limited for a specific range of Prandtl number, but Prandtl number could vary a lot. Let's say Prandtl number, which is mu over alpha, and is mu over rho, K over rho C, depends on the type of fluid that we are using. This is going to give us different values, and that shows the viscous diffusion divided by thermal diffusion. Now, Prandtl number for liquid metals that have a very high conductivity is going to be very small, so it's going to be 0.1. For liquid metals. For air, it's going to be 0.7. For water, we're going to see around 7. And for some oils, for some viscous oil, if the viscosity is high, the Prandtl number could be 2000 for some specific oil, or it depends on the oil viscosity. Now, through these empirical correlations and doing the fitting, dimensional analysis, graphical techniques, we can find out the Nusselt number that is valid for a wide range of Peclet number, and that's going to be 0.3387, Reynolds number to the power of half, Prandtl number to the power of third, divided by 1 plus 0.0468, divided by Prandtl number. This is going to be to the power of 2/3. Everything is going to be to the power of 1/4. And this Nusselt number is found empirically through the relying on experimental data for a wide range of fluids and stuff. And that's going to be valid for a wide range of Prandtl number. What we will do next, we will take the same approach of this using experimental data and empirical correlations to find out the convective heat transfer in addition to the flat plate for a flow over cylinders. So we will find out convective heat transfer. We looked at the flat plates. We look at the flow over cylinders and spheres, or flow across bank of tubes. And the last one is what we are using for the heat exchanger design.